Hello everybody, let's talk about section 3.2, which discusses polynomial functions of higher degree. Now, so far in this course, we've discussed polynomials, just some basics about factoring polynomials and something about polynomial functions. In the last section, we talked about finding zeros of polynomial functions using the zero factor theorem and other ideas that we've already familiar with. So what we're doing is we're taking this a step further, and we're going to discover some things about polynomial functions of degrees that are higher than 2. And how do we discover some of those behaviors about the function given what we know about the behavior of such curves? So our concentration here is to be able to identify far left and right hand behavior of the graph, what that means, determining maximum and minimum values on a polynomial function and how we can determine where those occur, finding real zeros of polynomial functions, something we've basically already covered, but using the intermediate value theorem as a tool, understanding the relationship between zeros, x-intercepts, and factors of a polynomial, and the behavior of even and odd powers of linear factors so that we can get a procedure in place to get a basic sketch of a polynomial function based on these behaviors. So what's the first thing that we have to know? Well, first of all, we want to know what kind of behavior we can expect from a polynomial. And the main behavior here that we're concentrating on is the idea that polynomial graphs are smooth, continuous curves. And what does that mean? A smooth, continuous curve is a kind of curve that we could potentially place our pencil down on one end of the curve and simply trace it all the way to the other end without ever once having to pick up the pen from the page. So we consider a graph that has that sort of characteristic to be smooth and continuous, kind of like this graph right here. Graphs that have points of discontinuity, graphs that come to sharp points and change direction suddenly, are all characteristics of functions besides polynomials. So we won't have to deal with any of these kind of problems where, let's say, we skip over a point or some other weird type of behavior. So those are all outside of our consideration. Well, the very first thing we want to consider is something about the far left and right hand behavior of these polynomial function graphs. What could we expect? Well, one thing that we can expect right away is that if we look at a polynomial just based on the leading coefficient and on the power, the degree of that polynomial, we can determine generally what's going to happen to the far left and right hand behavior of the polynomial function. When we say far left and right hand behavior, we're not interested in what happens in the middle of the graph around the origin. What actually happens as the graph goes further away from the origin to the far left or far right towards positive or negative infinity along the x-axis. Well, here's the rule. It says that if we have a polynomial of degree n, now don't worry about what all of these terms mean right here. This is a polynomial of degree n with a leading coefficient a sub n. The graph will have the following far left and right hand behaviors. We call this sometimes the leading coefficients test or leading term test. If we have a graph in which we have an even degree and the leading coefficient is positive, well then, kind of like the x squared graph, the graph will, as we go to the left towards negative infinity, tend towards positive infinity, and to the right, tend towards positive infinity. Now we can write the behavior this way, that as x tends towards negative infinity, there we go, y tends towards positive infinity, or as x tends towards negative and positive infinity, pardon me, we went to negative infinity already, as x tends towards positive infinity, y also tends towards positive infinity. On the other hand, if the degree is even, but we have a negative leading coefficient, then the behavior will be such that as we proceed to the left, the graph will go towards negative infinity, and as we proceed to the right, the graph will go towards negative infinity. So as x tends towards negative infinity, this is how we indicate this to the left, we could indicate that y tends towards negative infinity as well. And as x tends towards positive infinity to the right, y tends to negative infinity again. Well, let's compare that to what happens when the degree is odd, like a third degree or fifth degree. Well, if n is odd, then we know that as x tends towards negative infinity, y tends towards negative infinity. That is, to the far left region of the graph, the curve will tend towards negative infinity. We would write that as x tends towards negative infinity, y tends towards negative infinity. And on the other hand, as x tends towards positive infinity, the graph tends towards positive infinity as well. That is, as x tends towards the right, towards positive infinity, gets larger and larger in the positive direction, so does y. And you think a positive x cubed graph is a good example of this idea. If the degree is odd and the leading coefficient is negative, then we have the opposite behavior. That is, as x tends towards the far left-hand side, as x tends towards negative infinity, this time y will tend towards positive infinity. It goes the positive direction this time. And as we go to the far right-hand section of the graph, as x tends towards positive infinity, y will tend towards negative infinity. So this is what we call the leading coefficients test. It's actually very easy to handle. Let's consider the function p of x is equal to 3x to the fifth plus 4x to the fourth minus 2x cubed plus x squared minus 5x minus 1. What behavior can we expect? Well, we've got a positive leading coefficient. So it fits this aspect, and the degree is the fifth degree, so it's an odd degree. That is this behavior right here. So our behavior looks like it's going to be right here, identified as the behavior as x goes towards positive infinity, y goes towards positive infinity, as x goes towards negative infinity, as x goes towards negative infinity, y goes towards negative infinity. Well, how about our other function? F of x equals 3x minus 7x squared minus 2x cubed. Well, now this one, if we rewrite it in descending order so that our leading coefficient is first, negative 2x cubed, we write the terms in descending order, minus 7x squared plus 3x indicates that this is the kind of function that has a negative leading coefficient. So that is a negative leading coefficient like this one, and we have an odd degree. That's like this bottom behavior right here. And so we would conclude that that is the behavior of our graph. That as x tends towards negative infinity, y tends towards positive infinity. As x tends towards positive infinity, y tends towards negative infinity. All right, more in the next video.